is enzyme biosensor? An enzyme biosensor is an analytical device that combines an enzyme with a transducer to create a signal proportional to the target analyte concentration. Transducer will convert this signal into measurable response. A number of enzymes belonging to the oxidoreductase, lyase, hydrolase been combined with various transducers to create biosensor.
Okay, for enzyme biosensor based on pH electrode, electrochemical transducer are often used to monitor the enzymatic reaction by potentiometric or amperometric measurement of the product or co-substrate concentration. When the enzymatic reaction results in the change of pH, a pH electrode can be used as potentiometric transducer. Okay, there are different steps during the operation of enzyme sensor based on pH electrode. Okay, the steps are transport of the substrate from the bulk of the solution toward the enzymatic layer. Then diffusion of the substrate within layer accompanied by the enzymatic transformation of the substrate into reaction product with H+ production for consumption, migration of H+ toward pH electrode, and detection of H+ by the pH electrode. Okay, basically enzyme biosensor based on pH electrode mainly used in the in vivo application and the analysis of the food and beverage. Okay, so next is schematic diagram of the diffusion of the substrate S and the product P and H+ in the enzymatic layer of pH electrode. Okay, a schematic diagram representation of enzyme biosensor based on pH electrodes based on pH electrode is given in the figure. 1. The sensitive surface of the pH electrode is contact with an enzymatic layer and is immersed in a solution containing the substrate. The substrate migrates to the interior of the layer and is converted into reaction product with proton H+ production or consumption when it reacts with the immobilized enzyme.
Enzyme biosensor based on gas electrode. So what is the mechanism? The mechanism of this enzyme biosensor based on gas electrode is that gas probes are constructed using an ion selective electrode and a reference covered by a gas permeable membrane, and the gases diffuse from the sample solution through the gas permeable membrane, and it hydrolyzes in the thin film of the internal solution. So for the application, the enzyme biosensor based on gas electrode can detect urea concentration in detecting aspartate in food or supplement, and also can detect creatinine by using ammonia gas probe or carbon dioxide gas probe.
Okay, for enzyme biosensor based on conducting polymers have two different approaches to immobilize enzyme using conducting polymers. Firstly, the enzyme is entrapped within the growing ramified polymer network during its electrochemical formation, like the picture on this slide on the left. You can see that. And then second approach is you have two different procedure, which is first one is formation of a functionalized conducting polymer film, and then it will covalent binding of biocatalyst to the functionalities of the polymer surface. The applications of conducting polymers, I take the example of polypyrrole, which these applications is used to construct chemical sensors, photovoltaic cells, actuators, and electrochemical cells. Secondly, it will use as technological and biomedical applications.
Enzyme biosensor based on ion sensitive field effect transistor is one of the potentiometric biosensor. It is combinations of two well-developed techniques, solid-state integrated circuits and ion-sensitive electrode. The operational principle of ISFET is the formation of a potential difference at the width of the soft drain channel of the FET. The change of the FET characteristic, which is drain source current ID, will be a measure of the analyte concentration. Okay. So what is enzymatically modified ISFET? It uses pH-sensitive FET that insulator in metal oxide semiconductor such as silicon oxide was pH sensitive. During the enzymatic reaction in the enzyme membrane, protons are generated or consumed. The pH change as a result of the enzymatic reaction are measured via the pH FET and can be correlated to the analyte concentration.
Okay, next, I will explain about advantages and disadvantages of enzyme-based biosensor. First, the microstructure on the surface of the electrochemical biosensor can provide a variety of potential fields that can effectively separate and enrich the analytes, which can control the electrode potential, further improve the selectivity, and also combine the sensitivity of the determination method with the selectivity of the chemical reaction of the surface material. Second, the electrochemical enzyme sensor is an ideal system for the integration of separation, enrichment, and selective determination. Among them, the development of amperometric enzyme biosensor is the most representative and the most studied in biosensor field. Biosensors are developing to low cost, high sensitivity, high stability, and long life can meet the needs of field or on-site sampling and measurement. With the development of biosensor technology, it is necessary to reduce the cost of products and improve the sensitivity, stability, and life. The improvement of this characteristic will accelerate the commercialization of biosensors. Despite having many advantages, the development of a highly satisfactory enzyme biosensor is hampered because enzymes are not always stable. The instability problem can be circumvented by using enzymes stable at high temperatures, naturally available from thermophilic microorganisms. Furthermore, as the structure of enzymes become more defined, it is possible to tailor enzymes that can function under stress environment for a long period of time. Next, development of reagent-less biosensors involving enzyme reactions requiring diffusible cofactors such as ATP and NADPH is presently limited because of lack of methods for efficient cofactor regeneration. An efficient regeneration at a fast rate is feasible using designer enzymes in which the cofactor is anchored and can swing between the oxidation and reduction sites.
As for the past studies, for the pH electrode, there are studies about the direct measurement of organophosphate nerve agents. The pH electrode modified with an immobilized organophosphorus hydrolase, which is OPH, layer formed by cross-linking OPH with bovine serum albumin and glutaraldehyde. It's stable for at least 1 month when it's stored in pH 8.5 and 1 millimole HEPES plus 100 millimolar natrium chloride buffer at 4 degrees C. And for the studies for gas electrode, indetermination of L-aspartate was constructed by chemical immobilization of L-aspartate and is on an ammonia gas sensing probe. And the concentration range is 7.0 exponential negative 4 molar and negative 2 exponential negative 2 molar with a slope of negative 80, negative 58 decade, and the electrode was stable for more than 20 days. And for the ISFETS, their study in detect formaldehyde was developed using pH-sensitive field effect transistor FET as a transducer and alcohol oxidized from Hansenula polymorpha as a sensitive element. Response time is 10 to 60 seconds, and the operational stability is that not less than 7 hours, and the relative standard deviation is approximately 1 to 3%, and at 4 degrees C, the response was stable for more than 30 days.
In conclusion, the newly developed biosensors mostly rely on sensitivity, specificity, non-toxicity, small molecule detection, and cost-effectiveness. Enzyme biosensor has proven to be a valuable technique for the qualitative and quantitative analysis of a variety of target analytes in biomedicine, environmental, food quality control, agricultural, and pharmaceutical industry. In comparison with conventional analytical methodologies, the enzyme-based biosensors offer significant benefits such as miniaturization, real-time diagnosis capability, high sensitivity and specificity, minimum sample preparation, and high throughput bedside clinical testing and portability. That's all from our group. Thank you.